I'd like to introduce the speaker for today's event, uh, Guochang Wang. Guochang is currently an associate professor at St. Francis University. I think there's a little mistake on the title. I just didn't catch that, so my apologies. He is the professor at at St. Francis. He received his bachelor's petroleum engineering from China University of Geosciences in 2006 and his PhD degree in geology from West Virginia University in August 2012. He's then been a postdoctoral fellow and worked at the University of Chinese Academy of Sciences in Beijing for 2.5 years. He joined St. Francis University in March of 2015 and is now an associate professor at Petroleum Engineering and Natural Gas Engineering Department. His research focused on shale reservoir characterization through petrophysical analysis, 3D geologic modeling, SEM image analysis, seismic interpretation, machine learning, hydraulic fracturing simulation, reservoir simulation, and a variety of other techniques. So that's quite a long list there. But with that, I want to welcome Guochang.
Thanks, thanks, Brad. So,
and I'll stop sharing there, so you can go ahead and start.
Can you hear me?
Yeah, I can hear you just fine.
Okay. Yeah. So first, I want to thank Brian and also the Houston Geological Society to invite me to give this presentation. As Brian introduced, I'm an associate professor at San Francisco University. We are located in the central Pennsylvania. We are a private Catholic university. Our petroleum engineering program is only 7 years old. So we are quite young and quite a small program. Our campus is beautiful and we have very good students here. So welcome you all. If you have a chance to visit Pennsylvania area, please stop by. We would like to host you there. My talk today will be the 3D geological model of the shale reservoirs based on the horizontal wheel data. So here is my content. So I would first introduce why I want to do this research. As we all know, for the shale reservoir, we need to drill the horizontal wells and we need to do the hydraulic fracturing. And this is the technology we use to produce shale gas oil out. And because of that, we drilled a lot horizontal wells. And those horizontal wells, they are drilled in spatial pattern. Mostly they parallel with each other in their laterals in a spatial orientation. And those wells will be grouped in well paths. As you can see here, the left is the Bakken Shale and the right is the Utica Pond President. If you look at the other shales, they are quite similar for those horizontal wells, if they are in the core area of those shale oil or shale gas. And here's more examples for those horizontal wells. My point is there's a lot of horizontal wells was drilled in the history. We began to drill more horizontal wells than vertical wells now for the whole industry, not just for shale. In shale, exactly, there's more horizontal wells. And those horizontal wells, they are not really the straight line, they curve, they go up and down. And also our reservoir is not flat. The surface also goes up and down. This makes the situation for us to work on that very complex. And how to use those horizontal well data is very difficult. One reason is because most in the long history for our industry, we work on vertical wells. But the data in horizontal wells are very different from. So my next few slides will talk what's the difference between them. So first, the well trajectory. For vertical well, mostly they are even not a straight line, but it's very close to vertically. And they will penetrate through the formations vertically, almost. But horizontal well is very different. First is their trajectory will intersect with the formation surface at any angle between 0 to 90 degrees. You can see from the left here, they can go vertically, penetrate normal to the surface, and then change the angles. And then they can also penetrate the surface up and down also. Sometimes they go up downwards, sometimes they penetrate upwards. Make the angle between them could be any number. Sometimes we use negative number. Here I just use 0 to 90 degrees. If you argue that, okay, it could be from negative 90 to 90 degree, that's also reasonable. And also mostly because the target zone was within the reservoirs. Most will be the organic zones. So most of those horizontal wells will not penetrate through the base of the horizontal wells, the reservoirs, which is very different from the vertical wells. And because of that, our formation tops data will be very different also, which was the main data we used to build our geological models, especially the structural model. So first is you will see lots of repetition of the formation tops in horizontal wells. It's very common. Here, for example, you can see the top of the FM1. There's 3 points for that, and also 3 points for the FM2 top. But in vertical wells, except we have some reverse fault, unless you won't see those repetition formation tops. And also there's very limited data for the reservoir base. You can see here in this example, there's no data there at all. And also the lateral position of those formation tops is not at the same location as the vertical wells. They distributed along the horizontal wells. They're away from each other. This makes us very difficult to estimate the thickness of the shales. The reason of that is because most of the time we won't see the structure. We only see those horizontal wells with the formation data there. And neither the elevation difference or the measured depth difference works to estimate the thickness. Even a rough number is very challenging. And this is because the deep angle can also change for the formation surface. And also the thickness is another variables we need to assess. So you see here in these 2 pictures for the vertical wells in the left, we can easily to estimate the thickness, at least the true vertical thickness, the A1, or here the A2. To know the true stratigraphic thickness, or the real thickness of the shale, sometimes it's also challenging, but lots of time we don't need to know that. But for horizontal well, you can see in the right side, the thickness could be very different in these 2 cases. The left case here, you can see I just draw these 2 straight lines for the top based on the formation tops. But the other one, you can see if I change the formation deep angle, then the thickness could be very different from the left one. So this will cause some trouble. Also, for each surface, if we build the surface based on the formation tops, there's no trouble. We can make sure our formation goes through those tops. But if we make a multiple surface there in the 3D model, you can see between the surface, the distance could be very different from the real thickness of the shale. And this could be really away from each other or too close to each other. Sometimes even they will intersect with each other. This can cause some trouble. The main reason of this is because the location of those formation tops located at different positions. And this makes the interpolation of those surfaces very challenging. Another difference is for the formation tops we pick from horizontal wells is very challenging. This is a little bit out of those topics, so I just mentioned this. So there's higher uncertainty to use the horizontal tops in horizontal wells than the tops in vertical wells. There's also another data we usually don't use for vertical wells. Will be I call that a landing formation. That is show you here. You can see for the well like here between T9 and T8. This because this is the formation top. So here, this range here will be the let me show my pointer so I can point to that. So up here. So you can see here in these parts here. So if for these parts, we see this horizontal well is the landing formation for that segment is T9. And we can point lots of those landing formations. This information is not that useful for vertical wells. But for horizontal well, this is very useful. So I just call that a new soft data point for us to use for structural modeling. But in fact, they are there. We just don't use them. So let me give you a quick example. You can see how that works. For example, we build a surface for T4 top here, this green dashed line here. And our most of the software can make sure the surface will go through those formation tops in our wheels. There's no trouble for that. But the problem is, you can see in the right side here, the surface goes through this part here, intersect with the wheel in a wheel ball here. From the formation tops, they are correct. There's no trouble, but we know this is wrong, because if this is true, then part of our wheels go into the formations above T4, but really they should be low. And this is some new, that's the reason I want to use those information to build the 3D models, to check some errors especially. Also, the log data will be different. And because the logging methods, I just showed you this before picture. So you can see the log data in horizontal wheel, the logging methods, in fact, it matters different from the vertical wheels. For our vertical wheel, mostly we measure that the signal from laterals, but for what horizontal wheels, in fact, the signal is vertically come into the wheel ball, almost horizontal. And also, another big effect is for those horizontal wheels, looks like we are sampling at a spatial layers or several layers in a spatial zone there. So I call that a series biased sampling. So the sampling there compared to vertical wheel is very different, cause some trouble when we do some statistic analysis. So that's the difference of the data. So because of that, we developed some methods to build the 3D structure model and also the property models. So let's go to the structure model first. I call that like a battle between the thickness and the deep. So what's the thickness and what's the deep angle for those formation surface? We need to assess these two variables at the same time, which is quite challenging. So in 2008, when we work on the paper, we just published in APG Bulletin, we just make assumptions that the organic shale thickness only gradually change or has no change in a small area. And then we can make that easier for us to work on this. But if you work on a larger area with lots of wells there and the depositional system change a little bit, then the thickness will change. But we still assume they are only gradually change. But if you work on a path or a field path in a small area, we can easily to assume, okay, the thickness do not change. Or we can, then later on when we build the model, we can based on the horizontal wheels to assess the change of those thickness. But it becomes challenging and more difficult. So I want to give an example how we work on this. In this case, is a non-wheel there. We have one vertical wheel and the others are horizontal wheels. If you want, you can consider this like one pad. There's one wheel, there's multiple horizontal wheels. We also have a 3D sediment data, which help us to assess the formation surface a little bit. And also, we have lots of conventional logs in all horizontal and vertical wheels. And we divided the formation to 9 layers. You can see here, when we build the model, this is we use the methods very commonly used for the conventional reservoirs. With that, I mean we only use vertical wheels. But with that methods to build the structural model for shale reservoirs with lots of horizontal wheels, then you can see lots of troubles. For example, here in this part, the thickness you can see very different from the left. And there's a couple reasons for that. I will explain that later. And the data we have here, you can see this is the seismic data we use to interpret this surface. That's the base of the reservoir. Below that, we have another layer there as a limestone. And above those, there's the 9 layers there. So another example of cross-section you can see here, the thickness change a lot. You can argue that, okay, your interpretation from seismic data is not real. I think, yes, that's true. But the problem is, this is very common errors we have from seismic data, which has a lower resolution And also the uncertainty comes also from the velocity models people build. So it's very common to have a surface from the sediment data has errors on the elevation, or you can call that a deep angle. So this is another example in Marcellus Shale. You can see here, this is for two pads, in fact, we built. Again, we have one wheel there, and then this is the surface we built. Then you can find there are some wheels go up and down of those formations. It's very common. And so in 2008, we built the measures, which is we said, okay, we can put some pseudo-vertical wheels there to add more control at those formation surface, formation top location, and also infer their thickness based on the vertical wheel there. We assume the thickness do not change in that time. But later on in 2019 and 20 this year, we began to work on a larger area, the same area, but the data we have much, much more. And we thought, okay, there's some trouble for that method. So we improve this method. So this is the new we built, the methods. So we began to subdivide the formations to multiple layers, began to divide the pseudo-vertical wheel to 3 different types. The PVWA, which is we add the horizontal, the pseudo-vertical wheels add formation tops, or between, or when we check the errors, if we found some, we add another type of the pseudo-vertical wheels. So let me explain the steps one by one, then give you the examples. So the reason we submit those shale reservoir to multiple layers is because first, if you can have the data, I suggest you to do that because this will give you much, much more controls. You can see here, I use a dark shale example. It's not the real, that's just I made up those examples. So if you only have 2 formation surface you pick, there's only 2 data there available for the structure model. But if we subdivided those layers, upper dark and the lower dark to multiple layers, then the data points increased a lot. Think about if you have hundreds of horizontal wheels, the data increase is a lot. And by refine, this can also help us to refine the vertical position of the laterals. In the up case, you can see we only know, okay, the lateral was in the lower dark shale. But if we subdivide those, we can refine them to spatial layers in different locations. And this will help us in the future to work on those structural models. For example, this can reduce the thickness of those landing formations, or in fact, that's a layer. That's very useful for us when we work on the pseudo-vertical wheel B. And then for us to add the pseudo-vertical wheel A, mostly is we add that at the formation tops from horizontal wheels. And we don't want to add too many of those pseudo-vertical wheels. So we set a criterion like 200 meters lateral horizontal distance, or you can use 100 or 300. You can based on your area to judge those numbers. Because you can think about for this horizontal wheel, you can see here we add 7 pseudo-vertical wheels for this single horizontal wheel. So there will be a process, if you do manually, will be very time consuming. So we develop some program to do this. I will show you that later. And also for the pseudo-vertical wheel B is between those formation tops. You can see here, we added the wheels here. The difference from the A is we don't know exactly at the intersect points between pseudo-vertical and horizontal wheels. Where they are within the landing formations. But what we can know is we can figure out the limits, the upper limits and the lower limits based on the thickness and also the landing formations. Again, we developed the program to help us to work on this. Also, we don't add pseudo-vertical wheel B at all location based on this distance criteria. We only add the pseudo-vertical wheel B at the location we need to. That means we have errors there. So the main reason that is because there's a huge uncertainty because we really don't know where those formation top should be for the elevation, we don't know their range. So we need to make some assumptions. For the last step there will be the checking the errors. Mostly is if you build a model for shale reservoir, it's very common error is your horizontal laterals landing in a wrong layers in the 3D model. So we need to check those errors. Even we add the PseudoVertical where there's still some error there. So we need to check that. And then if we found error, we add the PseudoVertical wheel C there. So here is an example. You see for the shales we work on there. So first we add those PseudoVertical wheel A, and then we rebuild the model. And then we will compare the landing formations compared to the PseudoVertical wheel B if there's any error there. For example, in this case, you found this landing formation for this part should be in the yellow zones. But now some of that go into these blue zones. So we need to adjust this. So we add those formation types for this PseudoVertical wheel B. And later we check, okay, in our model, do we have any error there or not? Here is an example. You can see here, again, this horizontal wheel should be in this orange zone, but it goes to the blue zones. So we add another PseudoVertical wheel C here and add those formation tops to remove those errors. You can add more if you need, but our suggestion is we try to add least as possible to fix all those problems. And again, here is our program. We try to finish all those steps because if you do manually, again, it's very time consuming. And here is our the program. I use a VBA to work on this. The main idea there is to balance between the deep angle and the thickness. Even we assume the thickness in a small area, they don't change, but they still will have a little bit changing there. And with the formation surface, I mean the deep angle, we can assess the true thickness of those wheels from horizontal wheels. And then we can compare them to the vertical wheel. So the main idea there is the balance between the deep angle and the thickness. The other part will be the property model. This part is a little bit easier to work on. But the main idea behind is we try to assess the distribution fraction, the frequency for those properties, either like the porosity, permeability, or like the lithology or lithophysics. The first thing we work on the property model I want to suggest is for those log data, the data in vertical parts and horizontal parts is very different. So normalization is very necessary for that. And also the data quality control is also important because in those horizontal wheels, the wheel ball can change a lot. Those bigger or smaller, and then we need to remove some data there with a big diameter change of those wheel balls. The main trouble for us, in fact, to build the 3D property model is this, the bias samples in horizontal wheels. As I show you here, for example, these two, one is a vertical wheel and the other is horizontal wheel. The horizontal wheel looks like we are sampling in these parts. And this will make the distribution of those properties very different from vertical wheels. You can see here, the vertical wheel is this purple one. The blue color shows the histogram from horizontal wheels and vertical wheels. And distribution is very different. And for lots of those property modeling methods, they needed this distribution as an input. And this is another example we published in 2008 for those lithophysics, these discrete properties. You can see from vertical wheels and horizontal wheels, the distribution is very, very different. And for those property modeling, because especially for the data minimalistic methods like the kriging, distribution frequency is not that important. You can put that as an input, but not required. But for the stochastic methods, like the sequential Gaussian simulation for discrete properties, or for the continuity properties like porosity, permeability, saturation, we use the sequential indicator simulation. Those methods, those random methods, they need distribution frequency as an input to assess the overall distribution or the vertical distribution. And in those cases, those sparse problem is a problem to build the model. So we have two solutions. In 2008, we said, okay, we only use the vertical wheel data to do those. But later we found, okay, then the horizontal wheel data was not used. We waste lots of data. So what do we do for horizontal wheel? Now in 2020, the new method is we divided the horizontal wheels to many layers. And then we assess the distribution frequency for each layers. And also we remove some data if there's repetition or they not penetrate through the whole layers. So there's a filter layer we built. Let me explain this a little bit further. So first we divide the formation to many layers. And then if the wheel, for example, in the end, you see they don't penetrate through the whole layer, and then we won't use this data. Or like here, you see they only go into parts of that and go away. So we won't use those data. And also if there's a repetition even within one layer here, for example, you can see repetition, this layer, in a single layer, they go down and then go back and then go down. There's a repetition there. So we also remove those data. So we call that, mostly we build this with a filter we built. So here example, you can see this is horizontal wheel data. And then it's not that clear. Let me zoom in a little bit. You can see the top parts here, the green and red color shows the filter logs. Red means, okay, the data, whether they are repeated or there's some incomplete penetration. So we remove those data away. And then you can see the bottom one here, that's a QC we interpreted, the total organic carbon. So we remove parts of those data. And then we base on those filter data to assess its distribution functions. And the original property data, they serve as the constraint points. So this will maximize the data we can use to build a property model. And here is some examples you can see. Mostly you can see the big differences here in the top parts here in the legend. This shows the distribution of those property models we built. Here's the QC content. You can see this top one here without any filtering. We just use the data from the logs directly, and then we build the model. The bottom one here is we remove the repetition and rebuild the distribution functions. You can see the distribution for these two is very different. And the bottom one we believe is more close to the real case. Here is the lateral faces for shale. You can see the distribution for them also very different based on different distribution functions. And again, to do this, we develop a VBA property to work on this, to generate this filter. We need to have the structural model first, and then we can build these filters. So our structural model is very, very important for us to work on the property models, to make sure the horizontal wheel is landing in the correct layers. As a summary, we use different pseudo-vertical wheels for us to build the 3D structure models based on the horizontal data, the wheel data. And for the property model, we develop a layer-based access with the data filter layer to remove some data and also to maximum the use of the data from horizontal wheels. And for all those proper process, we develop some program to work on. There's many commercial softwares you can use to build the 3D models, but this proper program is help us to prepare the data to work with those commercial softwares. Here's some reference I used when I prepared this presentation, some pictures, and also our papers published there. Thank you for your attention, and if you have any questions, you can ask me now. Before that, I want to let you know we have a research center in our university. If you want us to help you to build some model or do some cooperation, we are more than happy to do that. So thank you. Any questions?
Yeah, thank you, Guochang. For questions, you should be able to see for all the attendees, there is a Q&A tab. If you go ahead and go into that Q&A tab, you could submit your question
Ah,
through that.
yes. Okay. Yeah.
And I did see one question was submitted right now. So if you want to go ahead and I can, basically the question is, how do you handle the directional survey cone of uncertainty?
Yeah, that's a very good question first. In fact, the first time when I present some related to this in APG conference, I think also in Houston a few years ago, people also asked me this, how to handle this one. Now I still think I don't have a really good answer to answer that. But my point is, generally, I will assume how those directional survey is correct. But there could be some error at the end, the toe parts of the wheels. And the answer there will be higher than the parts in the vertical parts or the beginning of the laterals. But for now, we don't have much method to handle this answer. In the future, I'm not sure I really will work on that or not, but one way we may do, but we have not, is to put a range for the data at the end of the wheel, the toe parts of the horizontal wheel. Give them a different number. But we have not worked on that, but that could be something we try to do.
Okay, awesome. Yeah, Gochen, I was also thinking of a question myself. I didn't type this one in, but whenever you're trying to map or pick tops interfaces along a horizontal section of a well with from I assume the gamma response, you made a point about the tool is now the response from the tool is now perpendicular or close to perpendicular to the layers versus a vertical well where it's almost quote unquote in parallel to some extent. So when that measuring aspect comes into play, you actually start to see effects of the layers as you approach them, but you still may be in the layer above.
Yes.
So how do you approach that whole process when you start to see that you might be getting a signal from two layers at the same time, even though you're still in formation above the one you're interfering with?
Yeah, very good question. So in fact, in our data, we also see those problems. Sometimes even they are in the same layer, but for example, the density, if you have some limestone there, the density change a lot sometimes, and also especially the PE values. And to work on this, in general, what we do is we will scan the logs one by one to see, mostly based on the PE curve. If we see a big change, we know, okay, it's not from the shale or it's from the other layers. We will just delete those data. And then, so most of these parts we can, if we have a very clear signal says those difference, then we can remove them. And also, if you don't see those and big difference, then mostly we assume, okay, they're from the same layer. And also, we will compare those horizontal data to the vertical wheels in the same layers to do some normalization. But again, here, if you work on the horizontal wheel log data, is very complex. There's still some uncertainty there. And even you do the normalization, even you remove some data, which you can see they from different layers, or even you can see from the picture here, even they mainly from the horizontal layers, for example, the shale, that's a that's like an average for the layers vertical. But in vertical wheel, mostly you measure the same layer. There's some lateral change for the properties, but mostly we can assume in a short distance they are the same. But for horizontal wheel, it's not. Even in a very short distance vertically, this also change a lot. So mostly we should with the log data in laterals as an average of a few layers vertical. Okay. So that will be something you need to consider. But again, we remove lots of data if we see they from different layers and then do the normalization.
Awesome. Got another question in here. Where do the thickness from the pseudo wells come from? As you said, it can be explained by dip or thickness, and geosteering interpretation is not unique. So what do you choose?
Yeah. So So in fact, I don't mention in this process is we do lots of iterations. So we don't build our model in one step. So we will build one model with only the whales from the data from horizontal whales and vertical whales. That will give us some error. Let me bring the picture there. So for example, here, at the first step will be this. So you have different way to do. For example, for this case, what we do is we assume the thickness is from vertical whales. We assume in a small area, if you work on that, you can assume the thickness there is constant. If you work on a larger area, as we just finished in 2009, last year, is we work on a larger area, we have around 10 vertical whales. So we just based on these 10 vertical whales to make an isopath map for those layers, all those layers. And then we based on that to make our first geostructure model, which is for those PVWAs. That's the thickness we use to make those formation tops. And then this will help us to make more contours for those formation surface. Then we can estimate the deep angle of those formation tops. And this deep angle come back to help us to reassess the thickness from the horizontal whales. And we continue to do this multiple times based on how do you confident with the thickness you use from the vertical whales. If you think, okay, the vertical whales don't give us a good assessment, then you may do more as iterations to reassess the thickness and also the formation surface, the structures there. I mean, and also then when you're good at that, then you can move to the next step for the pseudo-vertical beats to check any error there or not. Anytime if you put some formation tops, the deep angle will be changed. And then we will go back to reassess the thickness. So for example, for the example I show you here, I do 3 steps, iterations. And this works very well in this area is because it's very small. It's only have 8 horizontal whales, 1 vertical whale. If you work on a larger area, sometimes we do 6 or 7 iterations. We do multiple iterations to repeat to assess the thickness and the deep angle until you feel they are good. So our method, mostly we can make sure the horizontal whale will land in the layers correctly. But the thickness still have some uncertainty. And also the deep angle still have some uncertainty. So that's not really you have one step to build the model. In fact, there's multiple steps or iterations too.
Awesome. Well, Guochang, I'm not seeing any more questions show up right now live.
Yeah.
So if that's the case, I want to just go ahead and thank you once again for taking the time to visit with us today and present during your lunch hour. Thank you for that. We really, really do appreciate it. For those of you who attended and maybe want to share this talk later, we are recording the talk. It's a general rule of thumb for the Houston Geological Society for our live events that we don't publish these recordings to our YouTube channel until about a month after the talk. We just want to encourage people to actually attend the talk itself. So you will have that as support documentation later. And as you can see, Guochang's information is on the screen now. So please feel free to reach out to him via email or phone call, or if for some reason you don't remember or capture this information later, you can always reach out to the Houston Geological Society, and we have all that information as well.
Sounds very good. Thank you.
Yeah, thank you very much, Guochang. And with that,